Hi, Hal. Today I'll show you Excel sheet for doing a steel beam column design using IS800. So this Excel sheet, and here this is a place where you can give your input. This you can directly copy your like force from Stat Pro, so that you can design all the beams together, so you don't need to create individual sheet for it. And after the design, so before jumping into the design aspects and how the Excel sheet has been made, so let me just give like how IS800 has been organized. So before that, so yeah, let's say you have beam. So not beam, can count as any member. So if we call it as a beam, then it will have shear forces, and then along with that moment. Okay, and anything we call it as column when it has like only axial force. This we call it as a beam. Call it as a column. Okay, so here in beam will not have axial force. Okay, and in column, ideal column, we will not have any bending or shear. But when we make any framed structure, when we do analysis, then we will have all kind of forces in all the members. So what will happen in the beam, we can have like axial force. The nature of force may be like compression or tension. So while doing your design, so generally all steel members apart from partly all frame structure will be subjected to um, um, shear force and your moment, and then axial force. Okay, so all these forces will be there, so together we call it as a this one as a beam column. So same has been given in IS800. So which means that the like it will have a checks for your bending and your shear and your axial force, both whether it's like compression or tension. Okay, so this is how it has been. This concept is same for like any other code, so concept remains the same. Okay, so when we look into IS800, okay, so it's good to go through completely once what is there set at IS800. Okay, so that you will get to know what are the things are there. So here all the individual member in terms of the nature of load, considering from member like subject to tension, compression, and then comes with your beam design and then your beam column. Okay, so you'll be learning all the aspects. Okay, so when it comes to, yeah, let's say if it is your I section. Okay, so then okay, let me just copy this. Okay, if your I section, okay, so this I section, so this is your major axis and this is your minor axis. Okay, so let me just write this in a little bit. So the beam will be like this. not good in drawing. Okay, so this is how your beam will run. So the axis which cuts your beam here, right, this way I can say. Okay, yeah, the axis which cuts like this. Okay, this is your y-axis. Okay, and the axis which cuts the beam like two off here, so like it will be like this, it will become like this, like this. Okay, okay, so this axis we call it as a major axis. Okay, so here it will cut your beam along this way. Okay, so here, like generally when you are doing analysis, you'll find mz and my. Okay, this is we'll consider some major axis moment, and this is minor axis moment. Okay, so when it comes to major axis moment, the bending along z-axis, so means this is your plane. Okay, where it cuts the section top and bottom. So okay, so this bending, okay, bending along this way. Okay, this is your major axis force, and the similar way bending along the minor, this side. Okay, this we call it as a minor axis. So if you see in like plan, okay, okay, so if you see generally, like generally when we are writing, we are making, let's say if it is a beam, like let's say if it is simply supported. Okay, so this is what we write. Okay, this moment, this is the only moment we consider. So this moment we call it as a mz, that is a major axis moment. This is this one which is making the beam to go down on vertical you can call it as. Okay, and other one is along your, you can consider as a sideway, this side. Okay, so that's called the minor axis. Okay, so that's how the section has been classified. Okay, and then you can go for next important thing is your section classification. So currently we have like three classification: plastic, compact, and semi-compact. So here all the theory things has been given, so you can go through here and you can understand what is section. But the importance of classification is that, so like it helps if the member, like if a section, if it has sufficient thickness, then we can avoid local buckling. So thickness in terms of your unsupported length. Okay, let me take this snapshot, okay, to explain better. Okay, so let's say if it is your I-beam, then okay, so the ratio means like unsupported length. So here so the ratio of V by TF, that is uh, this cantilever part and the thickness, so it should be limited so that you can classify the section as based on certain values given in code. Based on that we can classify as plastic, compact, and semi-compact. So we have three um, uh, classifications. Yeah, for this section UB 254, so I can call as here buckling class we have to select, which is required for your when it checks for compression load. So you can select for like its role section, and like this has been linked with VLOOKUP, so we'll get all these values and have put the tables here, but these tables can be changed as per your requirement for the profile which you are using, and everything is comes here. Okay, and then okay, yeah, so here Okay, as I told before. Okay, so we need to check for both the web and flange. Okay, so one thing is, so we need to check, you consider this as an individual component. Okay, this one has one individual component and your web as like plate. You can consider as a plate. So what we are doing here is we are limiting the uh, like length to thickness. So we need to maintain certain thickness so that it will not fail locally. Okay, so yeah, so here it is um, yeah, so here it is b by tf. So in the excel sheet, yeah, if you go here, so we need to check for a web and as well as a um, flange. Okay, here what I've done here is I made a like function. Okay, function flange, and I'm passing this input, that's breadth, thickness, and your e is nothing but your root of sorry 250 by fy. There is a root of 250 by fy. Okay, so this, yeah, I'm passing here. So plastic is nothing but here, plastic section is nothing but here already the criteria has been given. So if it is less than 9.4 into see, yeah, so this I call it as sigma. I have forgotten the name of it. So sigma, so which I'm this value which I'm passing here. So b is nothing but b by 2, and all these values I have denoted, like I'm calling it as PL is nothing but 9.4, compression is 10 point multiplied by sigma. Okay, and ratio I'm doing is b by tf. So this is b which I'm passing. So how I'm passing here is, so function, see here I'm passing this breadth of the flange and thickness of the flange for flange calculation, and web for calculation. Okay, and this is a depth. Okay, neglecting the two flanges. Okay, so this value is square root of 250 by fy. So if it is fy is 250, then it's always 1. Okay, so based on that it will calculate if the ratio is less than 9.4 into e1. Okay, then it is considered as a plastic. Okay, let me just open and show you. Okay, you can use fight. Okay, debug, step into. Okay, so if you see, it's the values are appearing here. Okay, so b is nothing but like your b divided by 2, which is nothing but 73.2 something, and it's calculating your e is 1. Okay, so here is a ratio, your b divided by thickness of the flange, so you are getting the ratio 6.7. okay, and then so it is going here if the ratio is less than PL. So PL is 9.4, so our ratio, this ratio here, this is 6.7, so it is less. So the flange means the function what we are defining, we are checking the flange, so it classified as a plastic. So if you see the result, final result, it shows as a plastic. So the same thing will appear in your result here outside. It shows a plastic. A similar thing will happen for your web. So web has been defined here like 84, 105, 126 multiplied by your sigma. Okay, so here if it's for web, it is 84, 105, 126. Okay, and code suggests that you don't need to check for web shear buckling if d by t ratio is greater than 6 to 7 times. Okay, so when you're checking for web, okay, here you're checking for web, no, here. So if it is greater than 67, you don't need to check for web shear. Okay. So otherwise there is a clause where you need to check for shear buckling. Yeah, and this is for slenderness ratio limit. So this majorly we use it for when we're doing bracings, where it will be where we'll have only axial um, forces. So you can go through this, it will be very useful. And next comes, okay, so as you know, like design, we have both working stress method and limit state method. So currently, like in IS800 current versions, we are already moved to limit state. So working stress method we are not at all using nowadays. So we will have two criteria. So as you know, limit state of strength and limit state of serviceability. So limit state of strength is like when you are checking for the strength of the structure, and in serviceability, after structure has been erected, how it performs. So like after all the load has been applied, so we need to check for deflection and a few other criteria. Okay, so this is for your load combination, table 4, which is very important. Okay, and this is your partial safety factors. Yeah, so here comes your design of tension member. So design of tension member is like this is a like simple formula, stress strain formula what we use. So let me take a snapshot of it. Okay, okay, so here this is nothing but stress is equal to load by area. Okay, so load is nothing but, you can call it as, load is nothing but T. Okay, and your F will become your yield strength, Fy. Okay, area is nothing but Ag. Okay, so now we are checking for the capacity, so we can spike this. So if we just, so if we are calculating for this, we are calling it as a TDG, and then your Fy multiplied by your gross area, and then this is just addition, that's partial safety factor, just to make sure the structure is fine. So just we are dividing by some factor, so that like any variation during your like manufacturing stage, if there's any defect, just to take care of it. Okay, and any like okay, any, yeah, here you can find the partial safety factor for structure, so you can get it here. So for gone by yielding, so it's gone by yielding, so you can just only 10% is on. Okay, so the structure will be a little bit more safer. So the rule for connections, some checks has been given, so you can just go through all these things. Okay, and then comes your compression. So this or everything is involved in your beam design, so all the things are interconnected. So I'm just giving a brief introduction about it. Okay, even if you are, okay, even your compression, this also same thing. So if you just check it here, P, so P is nothing but your same formula, force is like your stress is equal to load by area. So this becomes your P, and this becomes your A, Fy, and this becomes your AC. Okay, here it is FCD. Okay, instead of your Fy, we are using FCD. So there are certain methods are given to calculate FCD. Okay, so here you can go through complete details. Okay, so we'll have need to go for find a buckling class as well. Okay, this is for finding a buckling class. Okay, so here certain limits has been given, so that based on that you can classify a buckling class, and then you can go back and you can find your, based on your KL bar ratio, you can find your FCD directly without using the formula which has been given here. So this is for effective length, and then what comes, yeah, so next comes the design subjected to bending. Okay, so here yeah, this is when any member like subject to bending. So okay, so we have to use this equation. So I'll just give how it has been formed. Okay, so this is your you can like a bending equation. I'll just put it here. So this we study in our engineering. Okay, so this is the same, like it has been related to here, so we don't need to remember this. It's pretty simple to simple equation. So here we don't need this part. Okay, so here we need m, this is your m equals f by I, okay, by y. Okay, so next m equals, so here zp, your section modulus, is nothing but I by y, f into z. Okay, so this is the equation. So to this you just add some additional masala, that is beta. So this factor we will get it from our section classification, what we did know. This is where it is helpful here. So this is coming here. So if the section is compact and semi-compact, so we are using this equation here, this value here, that is 1. If your section comes like shows a semi-compact, and when you're calculating your bending, you need to make it as a like a ratio of ZE by ZP, your elastic section modulus to plastic section modulus ratio. You need to find, you need to use that here, and that as usual we just need to put some additional factor of safety, partial factor of safety. So with that you got your bending equation. Okay, so here are some other fact things are there, so we can study this. Okay, and this is lateral and supported structure. Okay, okay, lateral and supported structure, like so any member which is not laterally supported, we can call it as lateral and supported. So which is not like it is unsupported, so that there will be additional torsional buckling in that. Okay, so you can check in Google lateral unsupported. Okay, here what it's showing, it is laterally supported. If you're seeing here this, okay, so this beam is laterally supported here. Now torsional buckling moment. Okay, so this equation you can use. Okay, and yeah, compression, this you can, critical stress, if critical, your if critical, so you can use either use formula, or you can use based on your slenderness ratio K by R. With that you can find directly F critical, or you can use this equation and then you can use here for finding your N critical. Okay, yeah. yeah, shear check. So as I told before, if it is less than 60, if our section classification when we're doing section classification, if the web, if it is less than 67E, then we don't need to check this. If it's more than, then we have to check this for your shear. Okay, so next thing what we are going for is beam column design. Okay, so this is all combined forces. So section 9 you will find all the numbers subjected to combined forces. Okay, combined shear and bending. Okay, so that's what we are checking. So here certain conditions are there, so you can go through that. And plastic and compact section is compact, then we have to use this equation. And if it's semi-compact section, we have to use this equation, where instead of plastic section modulus, we are using elastic section modulus. We are not considering still the plastic capacity of the section. Since it is slender, it will be weaker. Okay, and combined we are checking for the plastic and compact section. We are checking this, or either you can use any of this. Okay, so that is your moment with respect to capacity of the section. And of 1 or 2 you'll get it from here, constant beam table 17, so you can go and you can check there. So here certain condition has been given. And so bending and axial compression. So as I told before, so there are two things are there for any beam. Okay, for any beam we'll have shear, and then we'll have moment and axial force, which is in compression, and another axial, which is in tension. Okay, so we know that so at any instant of time you can have shear, bending moment, and compression. Okay, this is one case. Another one is at any instant of time you can have shear, bending moment, and your tensile force. So this forms another set, so we need to check for both. Okay, for this set and as well as this set. Okay, so here when we are checking for compression, when members subjected to bending moment, shear, and compression. So this is like what happens is when section subjected to compression along with bending, then what happens is it will try, compression always tries to like buckle the member, so it increases your like what you call like load on your section. Okay, so it will be very critical. So the beam, like we may need a higher section, but in the similar case, like when the beam is subject to tension and then shear and bending, so it tries to pull this side as well as this side. So what happens, it reduces your um, section requirement, and steel is good in tension, so it reduces your section requirement, so you can reduce weight of the structure if the members are subjected to tension rather than compression. Okay, so here in the Excel sheet, if you go by, so here you can see all the section classification has been done. So let's say if any section, like let's say if we are doing, if you're checking for flange and web, if it becomes both, or if the flange and web are plastic, then section will be considered as a plastic. But The same way, if the flange is plastic but the web becomes compact, like web becomes thinner, so then the total classification we have to consider the lesser one, so that is like compact section. Okay. Similarly, if it something becomes compact and it this another web becomes semi-compact, then section result will be like semi-compact. Okay. Okay, so here I have made like equation for calculating plastic modulus of different sections. So here you can see plastic calculation, sort of equation involved here. Plastic section modular calculation is like straight, like very easy one, so you don't have to put much effort in calculating it. So what is that like? Okay, plastic section modulus is ZP. So ZP is nothing but your area multiplied by the centroid. Very simple. Okay, let's say you have a rectangle section. What you have to do is find the centroid of the section. Okay, and then so centroid and centroid each have its own centroid. So let's say I will consider this as a A1 and this as a A2. Okay, and from the neutral axis, okay, this is my neutral axis. From the neutral axis, so this is my y. Okay, and similarly from here to here, this I will call it as y1 from here to here, and from here to here I will call it as y2. So what you have to do is just calculate this area here, okay, and the area here. So your ZP will become your A2 multiplied by okay, this one A2 I'll call it as Y2 just to be similar. So A1, okay, A1 multiplied by your Y1. So this is your ZP. It's very simple, and the same I have done here. So here if you see, you can find here. Okay, yeah, so yeah, next thing is so here in critical I am finding it, and shear capacity also we are calculating, and imperfection factor what we saw before. Okay, all these things you can find it in code. Design bending strength MD, so design capacity we are finding out, and then I'm finding interaction ratio. Okay, this is like what we saw here, interaction ratio value you can find, but like if it is a only beam, like if it is only has a what we call moment on major axis, then up to here it's enough, but generally will not have that. Will have what we call additional axial forces as well, so that also need to be checked, that you can find here. So here you can find, so moment it's taking, shear is taking, and interaction ratio both it's working fine. Okay, so I'm taking here both. Okay, considering both the considered value and which is given here, normal one. Okay, so here no tension, so it's showing as no tension. Yeah, and buckling class it's finding, and then you get final result here whether the section is like fine or not. These are all the parameters are there, so this you can find it in code. All these parameters are there here, all these parameter values and everything has been given here, so you can get it from here. And this is interaction again, this is here what is given, this interaction. Okay, and finally result. So for final result it's pass. So yeah, so that is the end of design. And here while inputting you can directly copy from STADA as well, or or you can type manually, you can put the values here. And one thing I want to tell is about effective length. Okay, even like the same design can be, you can do it in stat, but few consultancies or engineering firms, so they want to get it done manually. Okay, so in that case, for submission of, like for making a report and for submission, it will be very useful. Okay, so I want to uh, talk about a little bit about effective length. What is effective length? Okay, let's say you have, okay, okay, generally, okay, let's say you have a beam. Okay, it has L. Okay, this is the length. Okay, but effective length is nothing but certain, like generally, let's say if you have a RCC beam, just for example, when you are modeling in STAD, so it will be all center to center. Okay, like this is the length, but effective length will be only here, which is there inside, like outside to outside of the column. Okay, and similarly in steel, so you can find effective length. Okay, so effective length you can find based on the your end condition. Okay, so that was there in the beginning. I'll just show you. It depends on the type of end condition we have. So if the beam is cantilever, so then effective length we have to use 2 times the length of the section. So yeah, here you can see effective length. Okay, so if it is a cantilever, let's say if you're designing a cantilever, remember any cantilever member. Okay, any cantilever member. So here when you're designing, when you're considering a parameter, you should not design it for just what is the length given here. Okay, since it's a cantilever, it has to, we have to consider as a 2L. Okay, if the length is like 2 meter, so you have to consider that as 4 meter. Okay, that's effective length. And similarly, a lot of different conditions as given. Okay, so based on that you can find effective length. Okay, yeah, after you make all the design, let's say if you want a design report, since it is in like horizontal, so it is not in a like presentable format, because people like to check individually, and since you cannot accommodate everything here, what you can do is here serial number will be there, you can give serial number or serial number. So let's say if you want output for, if you want to design report for serial number 1, okay, then you can type 1 here. So if you go to design calculation, so you will get here. Okay, so let's say if beam id, I will give it as beam 1. Okay, beam 1, so same thing will come here. Okay, so for that, all the values, all your design report input, everything will be presented here. Okay, so you can put your title and then you can export. Let's say you already created this, so this is they call base sheet. So you'll have, let's say you have 20 beams, so what you can do, just you can export. So next sheet will be created with this beam number, whatever the number you are giving here, with the name number, everything will come here. Okay, so let's try for another one, beam 2. Okay, I want it's serial number 2. So here I'm giving the input serial number 2. Okay, I'll go here beam 2. So I'll just export this result. So beam 2 is created. So finally I can just print this out and I can submit for approval. And this saves a lot of your time in making individual beam design. And once it is done, like here you can see all the member failure and everything you can finalize in like a single shot. Okay, and here while working to make your work easier, I put some button like show input data. It shows only the things which you are inputting. So here we are inputting all these data and section and buckling class we have to select, and this moment gradient and equivalent moment factor which you can get it from code. So these are all input things what we are giving. Okay, and finally, like since it is like if I unhide, you'll have lengthier one. So if you just want to show view result, you don't want to see all these inside things, just check just press show result. So it shows only the results which you want would like to see and evaluate. Okay, so hope this Excel sheet is useful, and if you have any doubt, you can reach out to me, and keep watching. Thank you.